Hello everyone and welcome to another IB Physics video. Today we'll be looking at a paper 2 exam from May 2022, Timezone 1. So let's get started. In this first question, it says that a student uses a load to pull a box up a ramp that is inclined at 30 degrees. A string of constant length and negligible mass connects the box to the load that falls vertically. The string passes over a pulley that runs on a frictionless axle. Friction does act between the base of the box and the ramp. Air resistance is negligible. The load has a mass of 3.5 kilograms, so let's highlight that important piece of information right now. It is initially 0.95 meters above the floor. The mass of the box is 1.5 kilograms, and the load is released and accelerates downwards. Outline two differences between the momentum of the box and the momentum of the load at the same instant. Well, you would think, well, the speeds are the same. And if the speeds are the same, the only reason they would have different momentum is that one has a bigger mass, which means the magnitudes are different. Of course, you should probably mention because the velocities are the same and the masses are different. Second, momentum is a vector. The load is going down, the box is going at an angle to the horizontal. The directions are different. For part B of this question, the vertical acceleration of the load downwards is 2.4 meters per second squared. So you don't have to calculate the acceleration, it's already given. Calculate the tension on the string. Now, if you were to calculate the tension, you have to first calculate the net force on these two objects. So you can either calculate the net force on the load or the net force on the box. But you cannot use the net force on the box because the box not only has tension going up the ramp and force of gravity downwards, which means there's a component down the opposite direction. This also has friction, and you do not know what the component of friction is, so therefore you should not use the box to find the tension. We'll use the net force on the load because there's a tension upwards and a gravitational force downwards, and the net force should allow you to accelerate 2.4 meters per second squared. First, let's write down an equation for the net force. The net force, and we start with the sum of all the forces. We have the tension going upwards, positive, minus the weight going downwards because they're opposite directions. And this should equal to the mass times the acceleration. Using the values given in the problem, the tension is mass times gravitational acceleration times regular acceleration, which is 1.5 kilograms, 9.81 plus 2.4. And this will give us about 26 newtons. Once again, gravitational acceleration 9.81. The acceleration given the problem, 2.4 meters per second squared. Part C. Show that the speed of the load when it hits the floor is about 2.1 meters per second squared. So we have several of the initial conditions. We have the initial velocity. It is dropped to the initial velocity 0. We have the acceleration, which is given by the problem as 2.4 meters per second squared. We have the distance that it travels. Distance traveled is 0.95 meters. We did not know the time, and we did not know the final velocity. Now, it could find the time it falls and then use that to get the final velocity, or you can get the final velocity directly. In order to get the final velocity directly, you would use the equation velocity squared equals initial velocity squared plus 2as. Or if you want to find the time first, you would use distance equals ut plus 1/2 at squared. And then you can use any of the other three super equations to find the velocity. Regardless, if you use, let's say, the bottom one, just go one step, you'd get that the velocity is the square root of 2 times the acceleration 2.4 times the displacement of 0.95 meters. And that gives us 2.14 meters per second squared. Since it's a show that question, you have to use one more significant figure than the value that is given. Part D, after the load has hit the floor, the box travels a further 0.35 meters, and it travels along the ramp before coming to a rest. Determine the average frictional force between the box and the surface of the ramp. Now, first of all, let's separate the concept of the average frictional force and the net force. If you use the information given by the problem, the first thing you will find is that the net force, which would be the thing you calculate using the energies, is equal to the tension upwards minus the force of gravity down the ramp, which would be mg sine theta, as well as the force of friction. Now, how do you find the net force then? Well, there's two ways to find this. First, we can use either the energy considerations. So we can use the fact that the kinetic energy of the object as it hits the ground will be equal to the work done by friction. Since the friction has to remove all that energy from, the work done by the net force. Since this net force has to remove all the energy from the kinetic energy. So we have 1/2 the mass of the object times the initial velocity squared is equal to the net force on average times the distance that it travels further. This will make it 1/2 times the mass, which is 1.5 kilograms, and we said the initial velocity was 2.1 meters per second squared. And it should equal to the net force times the 0.35 meters. And we find that the net force should equal to 9.45 newtons. Now, what about all these other considerations? Well, first of all, its release of the tension is 0, which means these two forces are negative, but just means in the opposite direction that it was moving in. And when you add these two and get an absolute value, you should get the 9.45 newtons. So this is equal to mg sine theta plus the force of friction. So the force of the gravitational force down the ramp would be 1.5 times 9.81 times sine of 30 degrees, which would equal to approximately 7.4 newtons. So we have 9.45 equals 7.4 plus the force of friction. This implies that the frictional force should be about 2.1 newtons when you use two significant figures. Now, what happens if you use the Subat equations instead? if you use the Subat equations, you cannot find net force directly. You have to find the acceleration. And the way you find the acceleration is, well, you know the final velocity is 0. So if I find the velocity, it's initial velocity plus 2a s. Final velocity is 0. The initial velocity is, of course, the same as before, 2.1 meters per second. That means the acceleration is going to be negative. Just means in the opposite direction as the initial velocity. So you have 2.1 squared divided by the distance, which is 0.35. That would be approximately 6.3 meters per second squared. You can use this to find the net force. F net equals 1.5 times 6.3, F equals ma, which again is the same, 9.45. And from here, the rest of the solution is the same as before. Next, for party, the student then makes the ramp horizontal and applies a constant horizontal force to the box. The force is just large enough to start the box moving. The force continues to be applied after the box begins to move. Explain with reference to the frictional force acting why the box accelerates once the box has started to move. You have to do a comparison of the static friction coefficient and the dynamic friction coefficient. So I'll use symbols for here, but you should probably write this down. The static friction coefficient is greater than the dynamic friction coefficient. So therefore, the maximum static friction force is greater than the dynamic friction force. Therefore, after it starts moving, so after motion starts, the external force is greater than static friction force or dynamic friction force, which means the net force is greater than 0. So the way to explain this is this. To start it moving, first, the external force has to be at least equal to the maximum static friction force. But once it starts moving, the dynamic friction force is smaller than this maximum static friction force. So we have a net force. And of course, the last part is you reference the Newton's second law, F equals ma. Therefore, A is greater than 0, and the object accelerates. Next, question number 2. It says that cold milk enters a small sterilizing unit and flows over an electrical heating element. The temperature of the milk is raised from 11 degrees Celsius to 84 degrees Celsius. A mass of 55 grams of milk enters the sterilizing unit every second. The specific heat capacity of the milk is given here. Part A, estimate the power input to the heating element, state an appropriate unit for your answer. First, this statement here has to be converted to a specific set of variables. It's mass per second, right? So it's a change in the mass over change in time. In this case, the units are going to be 0.055 kilograms per second. Now, so if you want to know the amount of heat required to heat a specific amount of mass, you have amount of thermal energy necessary is equal to the mass times the specific capacity times the change in the temperature. But power is equal to the energy over time, which would mean the power here would be all of this divided by delta T. And the reason we do this is because this part's mass over delta T is exactly what you have here, the 55 grams per second. So let's input the numbers. It's 0.055 kilograms per second multiplied by specific capacity. 3.9 is kilojoules, so it's times 10 to the third joules per kilogram Kelvin, times the change in temperature, which is 84 minus 11. Using all these values, you get approximately 16,000 watts, which would be 16 kilowatts. Part B, outline whether your answer to A is likely an overestimate or underestimate to the power output. So what does this mean? In reality, if you use this amount of energy, some of this energy is going to leave because of thermal energy transfer. So you will actually need more energy to actually get it up to 84 degrees Celsius. So this is an underestimate. Because, or more power required. Because some of the energy is lost to thermal energy transfers to the environment. Or surroundings. Part C. Discuss with reference to the molecules in the liquid the difference between milk at 11 degrees Celsius and milk at 84 degrees Celsius. So it's higher temperature, right? Which means it has a higher average kinetic energy. So each molecule has slightly more energy because it's the kinetic energy on average is proportional to the temperature. So that also means that if it has higher average kinetic energy, it has higher RMS velocities. And what will also happen is it will have, they're moving around faster, they have more collisions per second. Or the average spacing increases. Or something to that effect. Anything that might result of higher velocities would be an acceptable answer here. For this next part of question 2, part D, it says that the milk flows through an insulated metal pipe. The pipe is at a temperature of 84 degrees Celsius. A small section of the insulation has been removed from around the pipe. Part 1, state how energy is transferred from the inside of the metal pipe to the outside of the metal pipe. Well, if we were to model this, let's say this is the metal pipe They're actually asking you is how it goes from here to here as it moves through the material of the pipe. It's going through a solid, so the only possible answer here is conduction. It does not actually ask you what happens, how it transfers from the pipe to the air, just through the material of the pipe. So it only considers the thermal energy transferring or going across the thickness of the pipe's material. On the other hand, if you see part 2, it says that the missing section of insulation is 0.56 meters long, and the external radius of the pipe is 0.067 meters. The emissivity of the pipe surface is 0.40. Determine the energy lost every second from the pipe surface. Ignore any absorption of radiation by the pipe surface. So we have to find the power of thermal radiation using Stefan-Boltzmann's law. Using Stefan-Boltzmann's law, the power of thermal radiation is equal to the emissivity, which is a fraction from 0 to 1, which tells you how well it emits thermal radiation, times the Stefan-Boltzmann constant, times the surface area of the object, times temperature to the 4th power. Now, only thing we have to do here is we have to calculate the area. The area is the circumference times the length. So it's going to be 2 pi r times the length. And we'll use this in this part of the equation. So, emissivity is 0.4. Stefan-Boltzmann constant, which is 5.67 times 10 to the negative 8 times the area, 2 pi, the radius, which is 0.067 squared, times the length, which is 0.56 meters, times the temperature to the 4th power, and it has to be a temperature in absolute value, or the absolute temperature, which is 357 Kelvin, which we'll put to the power of 4. Using all these values, we find that the power is 87 watts. Part 3. Describe one other method by which significant amounts of energy can be transferred from the pipe to the surroundings. Well, there's just 2 other methods. It can be either convection or conduction. So, convection, if you choose convection, you name it, and there's 2 points you have to explain a little bit more how it would happen, and that would be the pipe heats up the air around it. The air around it, when it is heated up, has less density, which means it flows away from it and is replaced by cold air. So, air around the pipe is heated. Or increases in temperature. And becomes lower density. And this rises because it's lower density. Then it's replaced by cooler air. Which is basically convection. Or you can also say conduction, which is just the flow of heat from the pipe to the air. Question number 3. 2 loudspeakers A and B are initially equidistant from microphone M. So there's speakers, A and B, and the microphone. The frequency and intensity emitted by A and B are the same. A and B emit sound in phase, so they should be able to interfere. A is in a fixed position, and B is moved slowly away from M along the line MP. So this is going to be important later on. The graph shows the variation with distance traveled by B of the received intensity at M. Part A, explain why the received intensity varies between maximum and minimum values. So, first of all, there's two wave sources, right? They meet at one point. So they will either they will interfere or superimpose in that point. So what's going to happen? Well, if the path difference is equal to an integer multiple of the wavelength, it constructively interferes and becomes higher intensity. But if the path difference is integer plus 1/2 times the wavelength, it destructively interferes and becomes a minimum. And because the speaker is moving away, the path difference changes, which means it will alternate between maximums and minimums. So as long as you mention all of these, the fact that there's two waves, that there's they interfere at a single point M, you have to also mention that they interfere or superimpose. And then you have to mention the conditions. And the fact is that because the speaker is moving, this path difference changes, and as it changes, it will alternate between constructive and destructive. Part B of question 3 says, state and explain the wavelength of the sound measured at M. First, you have to go back to the graph. You'll notice that it starts at a peak intensity because the path difference here is 0. It must be constructive interference. Next time here, the path difference must have been exactly one wavelength because it's the first time it has constructive interference. And it has traveled 26 centimeters. So therefore the path, with the wavelength should be also 26 centimeters. So we put wavelength is equal to 26 centimeters because the distance between peaks peaks of maximum intensity are one wavelength and according to the graph it's 26 centimeters. And if you would like, one other way to explain this is, in order to have constructive interference again, you have to move exactly one wavelength to be back in phase with the original wave. Next, for part D, it says that a loudspeaker A is switched off, so you only have one speaker left, and the speaker B moves away from M at a speed of 1.5 meters per second. There's a moving source. We must be using the Doppler equations, or the concept of Doppler effect. And the original frequency is going to be 3 kilohertz. Determine the difference between the frequency detected at M and that emitted by B. So it's a moving source. And it's moving away. So we use new frequency is the original frequency times speed of the wave over the speed of wave plus speed of the source. If you use the numbers given, it's 3000 hertz, 340 over 340 plus 1.5. Gives us approximately 2087 hertz, which means that the change in frequency, remember they asked for the difference in the frequencies, not the actual new frequency, it's going to be 13 hertz. A different way to get this, you can use the relative change in frequency is equal to the velocity over the speed of the wave, which is 1.5 meters per second over 340 meters per second, which must be equal to the frequency difference over the original frequency of 3000. Using this equation will give us the same result. For this next question, number 4, it says that a power supply is connected to 3 resistors, P, Q, and R, of fixed value, and to an ideal voltmeter. So we have the 3 resistors, P, Q, and R, and there's an ideal voltmeter connected like this. Our variable resistor S here is formed from a solid cylinder of conducting putty and is also connected to the circuit. The conductive putty is a material that can be molded so that the resistance of S can be changed by reshaping it. The resistance values of P, Q, and R are 40, 16, and 60 ohms respectively. The EMF of the power supply is 6 volts. So, first things first, this is the ideal voltmeter, so no current is going to go through that. You should probably just imagine that it's not there for now. Because one mistakes a lot of students make is they imagine this to be 2 parallel circuits in series, which is not true. What actually happens is, if you imagine that this path in the middle does not exist, you can imagine it as just being 1 parallel circuit with 2 resistors in the top side and 2 resistors in the bottom side. Like so. P, R, Q, and S. The resistance of P is 40 ohms. The resistance of R is 60 ohms. So let's erase this. Now, the voltage drop across P plus the voltage drop across R will equal to the full voltage drop because it's in parallel, so 6 volts. So whatever the voltages of P and R R, they will add up to 6. In fact, it's proportional to the resistances. Whatever has a higher resistance will have a bigger proportion of the voltage. So the voltage drop across P would be the total EMF times 40, which is the resistance of P, over the total resistance, which is 100. And the other one, the voltage drop across R, is the total voltage times the fraction of the total resistance, which is 60 over 100. And this works because if you do 40 over 100 plus 60 over 100, it's 100 over 100, which just gives you the total current, total voltage, sorry. So it's 6 volts times 40 over 100 is 2/5, and that would be approximately 2.4 volts. What about R? It would be 6 volts times 3 over 5, which would be 3.6 volts. And that makes sense. Adding them together should be 6 volts. So the potential difference is 2.4 volts. Now, since it's a 2-point question, of course, you have to show how you got that. It's the total EMF. Again, resistance of P divided by resistance of P plus resistance of R, which is 6 times 40 over 100, which is exactly the same equation that we used. B, the voltmeter reads 0. Determine the resistance of S. So if there's a 0 voltage difference here, it means that the voltage across here is the same as the voltage across P. So let's write that down. Here, the voltage drop at Q is 2.4 volts. And of course, that means the voltage drop across S is 3.6 volts. Now let's use exactly the same process that we used here. That means the voltage drop across S is 3.6, and it's a fraction of the total. So it's a total EMF times the resistance at S over the resistance of Q plus resistance of S. It's 3.6 is 6 volts times whatever resistance S has divided by 16 plus R. This becomes just a simple algebraic problem. The resistance should be about 24 ohms. Now, let's actually try to check it, right? This here was 2/5 of the total voltage, so it has 2/5 of the total resistance. This side here, R and S, should have 3/5 of the total resistance because it has 3/5 of the total voltage. So the question is 24 exactly 3/5? So 24 plus 16 is 24 over 40, which is indeed 3/5 of the total resistance, which is 3/5 of the total voltage, 3.6 volts. In part C, all the putty is reshaped into a solid cylinder that is 4 times longer than the original length. Deduce the resistance of the new cylinder when it has been reshaped. So recall, the resistance is equal to the resistivity, Greek letter rho, times the length divided by the cross-sectional area. So this leads you to the fact that it's going to be 4 times the length, but the cross-sectional area also is decreased. The volume is constant. So if we reduce, if we increase the area by 4, so the length, area times the length is the volume, by the way. If we make 4 times the length, it means you have 1/4 of the cross-sectional area. So you have 1/4 of the cross-sectional area, which means you have 16 times the original resistance, which is 16 times 24. So, which is about 384 ohms. In the second part of this question, it asks us to outline without calculation the change in the total power dissipated in Q and the new cylinder after it has been reshaped, basically the power through the lower branch or the lower path. So increasing the resistance means the total resistance of the lower path has also increased. Therefore, higher resistance means that the current is lower. Therefore, the power loss is lower. Since the power loss is equal to I squared times R. Or, because of the increase of the resistance, the power loss is lower because the power loss can also be the voltage squared over R, and the voltage is constant. The voltage is still 6 volts across both, right? Across both Q and S. So voltage is the same, but higher resistance. So the power loss is lower. Next, question number 5 says, A, describe the quark structure of a baryon. So, number 1, a baryon contains 3 regular quark. And it has to be only 3 regular ones because the opposite, the anti-baryon, is the one that has 3 anti-quark. You can also write that down, but you should probably give an example, right? Example, e.g., proton is up, up, down, neutron is up, down, down. An example gives you the other point, 2 points total. Next, you can use any of the properties of a baryon. For instance, there's an integer charge, integer multiple of E charge. You can also say something about it having a baryon number of +1. Now, there's 2 other possible answers that are technically true but not taught in the IB. You can talk about the spin. Or the fact that it is something called color neutral. But both of these concepts are technically not taught inside the IB. Part B. The Feynman diagram shows a possible decay of the positive cation meson. Identify the interactions that are involved at points A and B in this decay. First, let's label point A, and then there's a point B here. So what happens at A? At A, you have an anti-strange. It emits a positive boson, right? So if it emits a positive boson, this is, number one, it's a weak interaction. So when it says identified interactions, you have to either say strong, weak, electromagnetic. There are, unfortunately, no gravitational interactions in the standard model. What about B? In B, it's a gluon that decays into a anti-up and down. A gluon would be a strong interaction. Now, the fact that it's a gluon decay is not necessary. All you have to say, it's a strong interaction. The reason, of course, is gluons are only applicable to strong interactions, the same way as bosons being only applicable to weak interactions. Part C, the positive cation meson can decay as positive cation, making a positive muon plus muon neutrino. State and explain the interaction that is responsible for this decay. So it has positive cation and has neutrino. It must have been a weak interaction. Now you have to know the reasons for this. So one of the reasons is, number one, the positive cation has a strange particle or strange quark, and in this interaction, this strangeness is not conserved. Now, just as a side comment, this interaction they're talking about here in part C is not the interaction described by this Feynman diagram. Notice this Feynman diagram creates positive pions and negative pions, which is not the case here in C. So don't try to apply that diagram in this problem. Part 2. There is a neutrino involved. And whenever there's a neutrino involved, it means it can only have been caused by a weak interaction. Neutrinos are neutral, so it cannot be electromagnetic. And it's a lepton, so it cannot be strong. And lastly, there is a transfer of charge, which can only happen with omega plus bosons. For question number 6, a mass spring system oscillates horizontally on a frictionless surface. The mass has an acceleration a when its displacement from its equilibrium position is x. A variation of a with x is modeled in two different ways, a and b, by the graphs shown below. Outline two reasons why both models predict that the motion is simple harmonic when a is small. And here's the important statement. A is small, so you should limit your values to small values of acceleration around here in the center. And you can see when a is small, number one, the acceleration is proportional to the displacement and opposite in direction. So when a is small, acceleration is proportional to displacement. And opposite in direction. You can also say either negative, or it has a negative slope, and it's a straight line. So let's also add the alternatives. Straight line through origin and with negative slope. In this next question, it asks us to determine the time period of the system when the acceleration is small. First, in order to find the period, you have to use period is equal to 2 pi over the angular velocity. And in this case, remember that acceleration is negative angular velocity squared times the displacement, which is also negative k over m times the displacement. This implies that the slope of this graph above is going to be the angular velocity squared. So in order to find the angular velocity, you have to find the square root of the slope. So let's go back up to the diagram, and we have to put 2 points that will help us find this slope. So the gradient or slope, and let's say use this point here. The change in the y-axis is 1.0 over the change in the x-axis, which is 0.036, making this approximately 28. So the angular velocity is the square root of 28, but before we calculate it, we just input it here. 2 pi over square root of 28, making the period approximately 1.2 seconds. Next, part C of question 6, it says outline without calculation the change to the time period of the system for the model represented by graph B when A is large. So let's look back at graph B. What's the difference between graph B and graph A? Well, for large values, graph B has smaller values of acceleration. Let's write that down first. For graph B at large displacements, let's say, the acceleration is smaller. Let's just write like that. What would that do to the period? A smaller acceleration means you have a lower change in velocity, or smaller maximum velocity. And that means it takes longer, so a greater period. It takes longer to get to the equilibrium position because you have smaller acceleration, which means smaller maximum velocity. The graph shows the model A for the variation of x of elastic potential energy stored in the spring. Describe the graph for model B. So first, again, for graph for model B, acceleration is lower at large displacements, which means the force for model B is also lower. Which means the work done is also lower. And that also means lower work means the potential energy stored is smaller. So what it would look like if I were to draw here is up to a certain point, it will look almost the same, but then it will not go up as much. So for lower displacements, it would be almost the same. But for up to the larger values of the displacement, up to the amplitude, it will be lower values for potential energy. It's also acceptable to just draw this here, but you should probably also try to explain it using a sentence form. Question number 7. Two identical positive point charges x and y are placed 0.3 meters apart on a horizontal line. O is the point midway between x and y. The charge on x and the charge on y is positive 4 microcoulombs. Calculate the electric potential at O. So, electric potential is the Coulomb constant times the charge over the distance. Now, the net potential is just the sum of the individual potentials. So, potential to x plus the potential to y, which are basically the same because it's the same distance and same charge. So it's 2 times k q over r. Using the values, we would get 2 times 8.99 times 10 to the 9th with the Coulomb constant. It's microcoulombs, so 4 times 10 to the negative 6 coulombs divided by the distance being halfway is going to be half of 0.3, so it's 0.15 meters. Just calculating the first part here is going to be 2 times about 240,000. So net be 48,000 volts. And using kilovolts, 480 kilovolts. Part B, sketch on the axis the variation of the electric potential V with distance between X and Y. So let's just try to draw for one of them first. The potential would look like the 1 over X graph, kind of like this, and get closer and closer to 0 as it goes down. For Y, it would be the same thing. Kind of going the same way. And the sum of this would just look like that. Kind of like U-shaped. So this is what the sum would look like. You should not touch the 0 because it never goes to 0. You should have asymptotes at X and Y. And you could probably just draw it a little bit better like that. So it goes down, kind of goes a little bit more flat, like so. Part C, a positive charge Z is released from rest 0.10 meters from the origin, on the line between X and Y. Z then begins to oscillate about point O. Identify the direction of the resultant force acting on Z as it oscillates. So from here, it's being pushed towards O. And if it's on the other side, it will also be pushed towards O because it's oscillating. The force will always be towards O. As always. Number 2 says deduce whether the motion of Z is simple harmonic. Now, the electric force is KQ over R squared. This means it's not proportional, right? Because this is a reason. If it's not proportional, it cannot be simple harmonic. Question number 8, it says two capacitors C1 and C2 of capacitance 28 microfarads and 22 microfarads respectively are connected in a circuit with a two-way switch and a cell of 1.5 volts EMF. And it has a negligible internal resistance. The capacitors are initially uncharged. The switch is then connected to a position A. Part A, show that this charge stored in C1 is about 0.4 millicoulombs. First, if you are connected like so, only this one capacitor is actually connected, and only this one capacitor will charge. So we're going to use the charge in the capacitor is equal to capacitance times the voltage, which is 28 times 10 to the negative 6 farads times 1.5 volts. NA equal to 0.042 microcoulombs. Actually, what you would actually get is 4.2 times 10 to the negative 5 coulombs, which is 0.042 microcoulombs. For part B of this question, it says that the switch is moved to position B. 1. Calculate the energy transfer from capacitor C1. First, let's calculate the initial energy of C1. So the energy 1 initially be 1/2 times the capacitance times the voltage squared, which would be 1/2 times 28 microfarads, that's 28 times 10 to the negative 6, so times 1.5 squared. And this would give us about 3.15 times 10 to the negative 5 joules. And let's use this, change it to a little more convenient units, which would be 31.5, let's say microjoules. Next, let's get the final voltage of this capacitor. The way we can do this is we have the fact that at the end, the final voltages will be the same, but the total charge will equal to the total initial charge. So Q1 plus Q2 will equal to the total charge at the beginning. Of course, this was from the previous problem, 0.042 microcoulombs. We want to change this into units with voltage. So we know the capacitance is the charge per voltage, so the charge is equal to the voltage times capacitance, or the capacitance times voltage. This would be C1 times the voltage 1 plus C2 times the voltage 2. Now, the voltages are the same, so the final voltage, C1 plus C2, is equal to the final charge. This would be, the final charge was 0.042 microcoulombs, so it's times 10 to the negative 3 coulombs, divided by the sum of the capacitances, which is 22 plus 28 microfarads, so it's 50 times 10 to the negative 6 farads. This would simply be about 0.84 volts. Using that, we can get the final energy of capacitor 1. 1/2 times the capacitance times the voltage squared. 1/2, it's still 28 microfarads. But now it's 0.84 volts squared. And this would leave us with about 9.9 times 10 to the negative 6 joules, being 9.9 microjoules, which makes it easier to subtract initial minus the final. Give us the amount of change or decreased. So change in energy lost would be about 22 microjoules. Part 2 is to explain why the energy gained by capacitor C2 differs from this answer. And some of the energy is lost as it is transferred because you have a current and a resistance. Current is required to move the charges. There is a resistance to the wire. So some of the energy is compared to thermal energy in the wires. There's other ways to explain this. You can also say it would be transferred as electromagnetic radiation to the environment, or any such similar explanation would also be okay. In part C, a cell is now connected by a switch to a coil X, a second coil Y of cross-sectional area of 6.4 square centimeters, with 5 turns is looped around coil X and connected to an ideal voltmeter, as so. The switch is closed at time t equals 0. Explain how the voltmeter reading varies after the switch is closed. So first, we have this source of EMF, we have a switch here, and there is no current at the beginning. Closing the switch creates a current. So, initially, the voltmeter says 0. Next, the current will increase, which causes an increase in the magnetic field strength, which causes an increase in the flux. Increase in the flux means that there's going to be induced EMF in the coil Y. So there's a small peak when this happens. So which will then go back to 0 after the current is stabilized. Actually, the second coil is coil Y. Coil Y, yeah. So the EMF is only produced as the current changes. Once the current reaches its constant value, then we'll stop changing. There's no longer going to be any more induced EMF. In this following question, it says that the graph shows the variation with time t of the magnetic flux density B in the coil Y. Determine the average EMF induced across coil Y in the first 3 milliseconds. The induced EMF, on average, will be, there should be a negative sign here, but it's just absolute value for now. It's the number of turns times the change in the flux over the change in time. In order to find the change in flux, you have to get the magnetic field, the change in the magnetic field strength times the area with the change in time. Number of turns is 5. The change in the magnetic field strength here is 7.5 times 10 to the negative 3 because it's milliteslas. And the area would be 6.4 times 10 to the negative 4 square meters over the time, which is simply 3 times 10 to the negative 3 seconds. Using these values, we would get this to be about 8.0 times 10 to the negative 3 volts, which is 8.0 millivolts. For question number 9, potassium-40 decays by 2 processes. The first process is that of beta minus decay to form a calcium nuclide. A, write down the equation for this decay. So let's start with potassium-40. So it's 40, 19 potassium. It will decay into calcium, Ca, plus it's beta minus, so it's an electron, 0, negative 1. And if there's an electron, there must be an anti-electron neutrino, like so. This side, the number of protons has to equal to the sum of all the charges, so it's going to be 20. And still 40, the same number of nuclides. Next, part B. It says potassium-40 decays by a second process into argon-40. This decay accounts for 11% of the total decay of potassium-40. The rocks can be dated by measuring the quantity of argon-40 gas trapped in them. One rock sample contains 300 micromoles of potassium-40 and 12 micromoles of argon-40. Show that the initial quantity of potassium-40 in the rock was about 450 micromoles. So, the total amount of K that's decayed is going to be equal to the 12 micromoles over 0.11, which is 109 micromoles. Noise. So the total that originally was in there would be total K40 originally there would be the amount that we have right now, which is 340 micromoles plus the 109 micromoles, which would be 449 micromoles. In part 2 of this problem, the half-life of potassium-40 is 1.3 times 10 to the 9 years. Estimate the age of the rock sample. So we will use the simpler form of this equation, where the number of particles currently is equal to the initial number times 1/2 to the amount of time that has passed over the half-life. This simply becomes, this is the current number, which is 340 micromoles. This is the original number, which is 449, as given in the previous problem. You're going to divide them so we don't need the units. Equals 1/2 power of t divided by 1.3 times 10 to the 9. You should use logs for this. So this is 0.76, and you take the log of both sides, which base it is doesn't really matter. We'll go 2. Let's use base 2, because if you use base 2, you can get negative t divided by 1.3 times 10 to the 9 years. Otherwise, if you use base 10, you still have to do times log of 0.5. Whichever you feel it's easier. And the amount of time would be 5.2 times 10 to the 8 years. If you were so inclined, you can use the higher level equation. It's basically the same thing, except it's to the power of e to negative the decay constant times t. Using this equation just causes you to have an additional step where you have to find the decay constant as being, 1 second, the natural log of 2 over the half-life. This would be 5.3 times 10 to the negative 10 per year, so year to the negative 1. This is just an additional step, so I would probably recommend you to use the simpler form of this equation so you don't have to find the decay constant. But if you actually do find the decay constant, make sure to write it down, because you probably will use it in the next part of the problem. But part C says outline how the decay constant of the potassium-40 was determined in the laboratory for a pure sample of this nuclide. In order to find the decay constant, you have two options. You can either find the half-life first, but in this case that is not an option because the half-life is in the billions of years. So you have to use the equation where the activity is equal to the decay constant times the number of nuclides. So the decay constant is equal to the number of atoms in the sample divided by the activity. So you write that down on the sentence. Use the mass of the sample to determine the mass of the potassium-40 atoms, or the number of potassium-40 atoms, and divide that by the activity using a radioactive counter to get the decay constant. So you measure the mass of potassium-40 to get the number of atoms or nuclides, and then use or just measure the activity of the sample. And then use this equation. And that is it for today. Thank you for watching, and see you next time.